Hi, Mr. Gibson here. Today we're going to look at geometric series. This is the fifth lesson in this unit on sequences and series and our final lesson. So far we've looked at arithmetic, sequences and series, geometric sequences, and so now we're going to look at geometric series. So let's look at our objectives for today. First one is, how do we evaluate a finite geometric series? And if you remember from the previous lesson, when we say evaluate, we mean to find the sum of all the terms. But notice we have two different cases here. We have finite and infinite. So we're going to look at both cases, right? When we have a certain number of terms, how do we find the sum or evaluate? Or if we have an infinite number of terms, can we, and if we can, how do we evaluate or find the sum of an infinite number of terms? So let's do a little review again. Series is the expression for the sum. So again, the key thing, if you see me asking for you to find or evaluate a series, I'm asking you to find the sum. And we have two cases. We just talked about this, right? We have a finite specific number of terms, and we have infinite. So let's look at some examples. We've seen these before. Here would be a finite sequence, 5 terms. Here's what that would look like if we rewrote it as a finite series. We have, again, 5 terms. And if you look at this, this would be geometric, right? We're multiplying by 2 each time. The common ratio would be 2. Here's an infinite sequence. We can tell by the ... Right? That tells us it goes on forever. And then here is a finite series. Same thing, ... tells us that it goes on forever. So these are all geometric, right? They all have the same common ratio of 2. All right, let's move forward here. Clear this. So first, I'm just going to give you the equation for the sum of a finite geometric series. Okay, and the key here is that this is finite. All right. So notice our equation has to have n in it, the number of terms, right? And there it is right there, n. Okay. The rest of these we should be pretty familiar to us now. So we have n, right, the number of terms. A1 is the first term, and r is the common ratio. And as we've seen before, we can't let r equal 1, because therefore it would not be a geometric sequence. If we multiply by 1, we just get the same value each time. And in this case, if you look at the equation, you see that if we put 1 in for r, right, this would become 0. And we cannot divide by 0, right? So we don't want this to be 0. That's why we have this restriction over here. R cannot be equal to 0. All right, let's look at some examples where we can apply this equation. Here is the series I'm asking you to evaluate: 3, 6, 12, 24, 48, 96. Here's the formula we're going to use. It's kind of messy. So this is definitely plug in the numbers, but then use your calculator. But we got to be really careful with order of operations here. What do we do first? What do we do second? So the 3 terms or values that we need is n, the number of terms. So we can see that we have 6 terms that we're going to sum up here. So n will be 6. The first term we need, which is simply 3. And the common ratio, right, we need to figure out what our common ratio is. So remember, the best way to do that is to simply take the second term and divide it by the term before it. So 6 divided by 3, that gives us 2, right? And just check, let's do it one more time. 12 divided by 6, and we also get 2. Okay, so always good to check a couple pairs of terms to confirm our common ratio. So our R value is 2. All right, let's plug all that into the equation. Now, what do we do first, right? Think of order of operations. What can we do inside the parentheses? Well, we have one set of parentheses, and we have subtraction, and we have exponents. So we're going to do the exponents first. So 2 to the 6th is 64. Make sure you know how to raise any number by another number on your calculator. Now, most calculators have a key that looks like this, y to the x, okay? So look for that key. Generally, what you would do is you would put in the 2 first, right? Then hit this function, y to the x, and then put in 6. So what this says we're doing, we're taking 2, right, and raising it to the 6th power. It might look like that on your calculator. And we get, as we see below, 64. Okay, so make sure you know how to use that function key on your calculator. How do we raise one power or number to any other number? All right, so let's continue on here. The next thing we want to do is what's in the parentheses, right? 1 minus 64. So we're going to get a negative 63, right? Subtracting 1 and then change the sign. And now let's finish it up, right? The negative 1 and the negative 63 is just going to give us a positive, and we multiply that by 3, and we get our answer. Oops, 189. Okay. All right. So there's an example of how to use the formula to evaluate a finite geometric series where we have a limited number of terms. All right, let's do another one here. I'll hit pause, see if you can do this yourself. Okay, here's the formula. And again, we need to find n. So in this case, n is 6 again. First term is 1. Common ratio in this case, pretty easy to recognize, right? We're multiplying by 2 again. So we actually have similar values that we had in the previous problem. The only difference is our starting value. So let's plug it all in. 2 to the 6th again gives us 64. We're going to get a positive 63 when we divide by negative 1 and then multiply by 1. Won't change that. So our final answer is positive 63. Right, here's another one for you to try. Now be careful with the negative and positives, right? Let's figure out what the common ratio is by dividing the second term by the term before it. Okay, let's set this up. Same formula. We have 5 terms. First term is negative 4. And in this case, let's go ahead and together find the common ratio, right? So our common ratio is going to be equal to 12 divided by the negative 4, which gives us a negative 3, okay? And if we did the same thing, right, we'd have negative 36 divided by a positive 12, again, gives us a negative 3. All right, so there's our common ratio. Let's plug everything in. Negative 3 to the 5th power, your calculator can handle the negative, gives us a negative 243. Now, inside the parentheses, we have 1 minus a negative. So subtracting a negative, remember, is the same as adding a positive. So that becomes 244. The 4's divide out, and we just are left with a negative 244. So these will take a little space on your paper to work out. I recommend kind of showing some of the intermediate steps, especially when you do the first few of these. Eventually, you might be able to just do all of this directly in your calculator. All right, last one here. We'll see if you can do this. All right, common rate or number of terms 5, first term 5, and our common ratio is 3. We're multiplying by 3 each time. So we plug all that in. We get 3 to the 5th again, 243, but we're subtracting that from 1. So we get negative 242. Grab a calculator and finish this up. We get a positive 605. Okay, so there's some examples how to use the formula to evaluate a finite geometric series, meaning we have just a specific number of terms. Okay, and this formula, make sure you have that in your notes and labeled, right, as the sum of a finite geometric series. All right, so let's shift gears and talk about an infinite geometric series. Okay, so this is the key question. We know we can add up and find the sum of a finite number of terms, but is it possible to find a particular sum for an infinite number of terms? Because our first thought would be if we just keep adding an infinite number of terms up, we're going to get an infinite answer. So let's see what happens here. Here's a geometric sequence, 1/2, 1/4, 1/8, 1/16. Each time we are multiplying by 1/2. Right? Let's go ahead and write that in here. Our common ratio would be 1/2. Okay. All right. So what do we think the sum would equal or approach as we continue to add more and more terms? Well, let's do this graphically, right? Here's a square. Just notice these are all fractions. So we can begin filling in the square based on the fraction. It's just another way to graphically add them up. So the first term is 1/2. That's going to fill up half of our square. Then 1/4. Then 1/8. So you kind of get the idea here, right? We're going to take the remaining area of the square and keep filling in half of it at a time, right? 1/16, 1/32, 1/64, etc. So what do you think is going to happen as we continue to do this, filling in the remaining half, and as we do this an infinite number of times? Well, I think you can see what's happened, right? Eventually, we are going to come very close to filling in the entire square. So the square, remember, it started out as a square of unity, meaning a side of 1 for each one. So the area of this total square would be 1. In other words, if we kept adding up an infinite number of terms in this geometric series, the sum would eventually equal to 1 or approach 1. All right, so remember, we said an infinite series continues without end. So how do we tell whether or not we can evaluate it? Because here's the thing, not all infinite series can be evaluated. They do not all have a finite sum. So let's look at 2 examples and see if we can figure out a rule for how we can tell whether or not we can evaluate a infinite geometric series. So the first one, what if we were to graph, right, the sum as we continue to add more and more terms? Well, let's do it here. Notice we would get a graph as we add 3, then 6, then 12, then 24, etc. And we continue to do that. This graph is just going to get larger and larger and larger. So in this case, the sum would be infinite, right? And looking at the terms, we could tell we have a common ratio of 3. So a new word we're going to be using is this word diverge. Okay, what does it mean to diverge? Diverge means to get further and further apart, or to just kind of keep getting larger and larger. So we say that when the value of an infinite geometric series is infinite, it just keeps getting larger and larger. Another word we could use to describe that is diverge or diverges. All right, let's look at our other example here. Same thing, we're going to add up these terms. So 8 plus 4 plus 2 plus 1, and notice has a very different shaped curve. And if we continue to do this, this curve is eventually going to flatten out, and it's going to flatten out at a value of about 16. Now notice in this case, our common ratio is 1/2 or 0.5, right? We're multiplying by 0.5 or dividing by 2 each time. So in this case, when we see that the sum is going to approach a finite value, in this case, right, 16, we continue to do this, we're going to get closer and closer to 16 as our value. We say that it converges. Okay, so these two new terms we have, diverge means it gets infinite, converge means it approaches or gets closer to a finite value. Now notice the one that diverged had a common ratio of 3. The one that converged had a common ratio of 0.5. Well, how could we describe the difference between these? Basically, this has a common ratio that is greater than 1, the one that diverged. The one that converged, the common ratio was less than 1. Okay, so this is going to be very important criteria that we can look at and then decide whether or not an infinite geometric series is going to converge or diverge. All right, so let's put this into a definition. Here it is. Evaluating infinite geometric series. If the common ratio is less than 1, and notice we're taking the absolute value, so we don't care if it's positive or negative. The key is if it's less than 1, then we say it converges and we can find the sum. Okay, so if it's less than 1, it converges and we can eventually find the sum. If it's greater than 1, then it diverges and it approaches no limit. In other words, it will eventually become either positive or negative infinity. So let's look at some examples and see if we can determine would these series converge or diverge. Well, to do that, we have to find the common ratio. So let's just step through these. See if you can figure out, hit pause, and find the common ratio and then decide which case we have up here, converges or diverges. Okay, so A has a common ratio of 5, right? 5 divided by 1, 25 divided by 5 gives us 5. That is greater than 1, so it diverges. Let's look at B. 6 plus 2. So if we divide 2 by 6, we get 1/3. So our common ratio is 1/3. It's less than 1. So in this case, we would say it converges. Let's do C. Here we get a common ratio of -1/2, right? -8 divided by 16. So it would converge. And then the last one, we have a common ratio of -3. The absolute value is greater than 1. Again, we don't worry about whether it's positive or negative, and we see that that diverges. All right, now there is a formula we can use to find the sum of an infinite geometric series as long as it converges, right? So the sum of an infinite series, but as long as it converges, meaning the common ratio has to be less than 1. So this is the only time we can use this formula, is if the common ratio is less than 1. So let's look at a couple examples and then we'll wrap up this lesson. Here's our series, 8, 4, 2, 1, 1/2, 1/4. Okay, what is our common ratio? Well, let's find it. R is going to be equal to 4 divided by 8, which tells us 4 divided by 8. We can simplify that to 1/2, or if you like decimals, right, 0 0.5. Okay, so that means it's less than 1. We can use the formula. The infinite series will converge. So let me clear my annotations here. So here's the equation. Now notice we just have two values, the first term and r. This one's simpler than the earlier equation I gave you. So let's plug in our values. In this case, we already figured out r is 0.5. So we're going to put in 8, the first term, divided by 1 minus r, or 0.5. So 1 minus a half leaves us with a half. 8 divided by 0.5 gives us 16. Okay, so if we continue to add these numbers up, they eventually will equal or come very, very close to 16. Here's kind of what that would look like graphing, right? This was similar to an example we saw earlier. All right, one more example here. 3, negative 3 halves, 3 fourths, negative 3 eighths. What is our common ratio here? Let's figure it out. So we're going to say negative, right? 3 halves divided by a positive 3. Now, I'm going to write that 3 as a fraction, because really what we're doing is dividing one fraction by another fraction. And if you remember, the way we do that is to multiply by its reciprocal. So we would have negative 3 halves times, right? Now let's take the reciprocal, 1/3. So the 3's divide out, and we're left with a negative 1/2. Okay, so there's our common ratio. So let's plug that in. Here's our negative 1/2, or we could use negative 0.5. And now we're going to be subtracting a negative, which is the same as addition, right? So we have 3 divided by 1.5, which simplifies to 2. So here's what it would look like, right? We'd start with 3 and then add negative 3 halves. Notice it's going to kind of move above and below this value of 2, but eventually settle down and converge or come very close to the value of 2. All right, so that's it. We now know how to evaluate a finite geometric series, right? That was the first equation that we had. And then we know how to evaluate an infinite geometric series. But here's the key, right? We can only do this if, right, the common ratio, absolute value, is less than 1. As long as it's less than 1, then we can evaluate an infinite geometric series. All right, that's it for today. Thanks.